Good day, this is Professor Will, CBMD PhD, and today is Monday, April 13th, 2020. It is 8:32 and 41 seconds p.m. Eastern Standard Time, and this is the final session on cosmology and black holes. So let's get started here. A second discovery provides even more compelling evidence. X-ray astronomers have detected a spectral line from one galactic nucleus that indicates the presence of atoms near the nucleus that are moving extremely fast, about one-third the speed of light. Furthermore, the radiation from these atoms has been redshifted in just the manner one would expect for radiation coming from near the horizon of a black hole. And if they were verified, then the hypothesis that some galaxies contain supermassive black holes at their centers would be fairly secure. A completely different class of black hole candidates may be found in our own galaxy. These are much lighter stellar massive black holes, which are thought to form when a massive star ends its life in a supernova explosion. If such a stellar black hole were to be off somewhere by itself, we wouldn't have much hope of finding it. However, many stars come in binary systems, pairs of stars in orbit around each other. If one of the stars in such a binary system becomes a black hole, we might be able to detect it. In particular, in some binary systems containing a compact object such as a black hole, matter is sucked off of the other object and forms an accretion disk, the stuffing swirling into the black hole. The matter in the accretion disk gets very hot as it falls closer and closer to the black hole, and it emits copious amounts of radiation, mostly in the X-ray part of the spectrum. Many such X-ray binary systems are known, and some of them are thought to be likely black hole candidates. Suppose you found an X-ray binary system. How can you tell whether the unseen compact object is a black hole? Well, one thing you'd certainly like to do is estimate its mass. By measuring the orbital speed of the visible star together with a few other things, you can figure out the mass of the invisible companion. The faster the star is moving, the stronger the gravitational force required to keep it in place, and so the more mass of the invisible companion. If the mass of the compact object is found to be very large, then there is no kind of object we know about that it could be other than a black hole. An ordinary star of that mass would be visible. A stellar remnant such as a neutron star would be unable to support itself against gravity and would collapse to a black hole. The combination of such mass estimates and detailed studies of the radiation from the accretion disk can supply powerful circumstantial evidence that the object in question is indeed a black hole. Many of these X-ray binary systems are known, and in some cases the evidence in support of the black hole hypothesis is quite strong. Many of these X-ray binary systems are known, and in some cases the evidence in support of the black hole hypothesis is quite strong. In a review article in the 1992 issue of Annual Reviews of Astronomy and Astrophysics, Ann Cowley summarized the situation by saying that there were 3 such systems known, 2 in our galaxy and 1 in a nearby large Magellanic Cloud, for which very strong evidence exists that the mass of the invisible object is too large to be anything but a black hole. There are many more such objects that are thought to be likely black holes, on the basis of slightly less evidence. Furthermore, this field of research has been very active since 1992. The number of strong candidates by now is larger than 3. How do black holes evaporate? This is a tough one. Back in the 1970s, Stephen Hawking came up with theoretical arguments showing that black holes are not really entirely black due to quantum mechanical effects. They emit radiation. The energy that produces the radiation comes from the mass of the black hole. Consequently, the black hole gradually shrinks. It turns out that the rate of radiation increases as the mass decreases. The black hole continues to radiate more and more intensely and to shrink more and more rapidly until it presumably vanishes entirely. Actually, nobody is really sure what happens at the last stages of black hole evaporation. Some researchers think that a tiny stable remnant is left behind. Our current theories simply aren't good enough to let us tell for sure one way or the other. As long as I'm disclaiming, let me add that the entire subject of black hole evaporation is extremely speculative. It involves figuring out how to perform quantum mechanical, or rather quantum field theoretic calculations in curved space-time, which is a very difficult task and which gives results that are essentially impossible to test with experiments. Physicists think that we have the correct theories to make predictions about black hole evaporation, but without experimental tests, it is impossible to be sure. Now, why do black holes evaporate? Here's one way to look at it, which is only moderately inaccurate. I don't think it is possible to do much better than this. unless you want to spend a few years learning about quantum field theory and curved space. One of the consequences of the uncertainty principle of quantum mechanics is that it is possible for the law of energy conservation to be violated, but only for very short durations. The universe is able to produce mass and energy out of nowhere, but only if that mass and energy disappear again very quickly. One particular way in which this strong phenomenon manifests itself goes by the name of vacuum fluctuation. Pairs consisting of a particle and antiparticle can appear out of nowhere, exist for a very short time, and then annihilate each other. Energy conservation is violated when the particles are created, but all of that energy is restored when they annihilate again. As weird as all of this sounds, we have actually confirmed experimentally that these vacuum fluctuations are real. Now, suppose one of these vacuum fluctuations happens near the horizon of a black hole. It may happen that one of the two particles falls across the horizon while the other one escapes. The one that escapes carries energy away from the black hole and may be detected by some observer far away. To that observer, it will look like the black hole has just emitted a particle. The process happens repeatedly, and the observer sees a continuous stream of radiation from the black hole. Won't the black hole have evaporated out from under me before I reach it? We've observed that from the point of view of your friend Penelope, who remains safely outside the black hole. It takes you an infinite amount of time to cross the horizon. We've also observed that black holes evaporate via Hawking radiation in a finite amount of time. So by the time you reach the horizon, the black hole will be gone, right? Wrong. When we said that Penelope would see it take forever for you to cross the horizon, we were imagining a non-evaporating black hole. If the black hole is evaporating, that changes things. Your friend will see you cross the horizon at the exact same moment she sees the black hole evaporate. Let me try to describe why this is true. Remember what you said before. Penelope is a victim of an optical illusion. The light that you emit when you are near the horizon but still on the outside takes a very long time to climb out and reach her. If the black hole lasts forever, then the light may take arbitrarily long to get out, and that's why she doesn't see you cross the horizon for a very long, even an infinite time. But once the black hole has evaporated, there's nothing to stop the light that carries the news that you are about to cross the horizon from reaching her. In fact, it reaches her at the same moment as that last burst of Hawking radiation. Of course, none of that will matter to you. You've long since crossed the horizon and been crushed at the singularity. Sorry about that, but you should have thought about it before you jumped in. What is a white hole? The equations of general relativity have an interesting mathematical property. They are symmetric in time. That means that you can take any solution to the equations and imagine that time flows backwards rather than forwards, and you'll get another valid solution to the equations. If you apply this rule to the solution that describes black holes, you get an object known as a white hole, since a black hole is a region of space from which nothing can escape. The time reverse version of a black hole is a region of space into which nothing can fall. In fact, just a black hole can only suck things in. A white hole can only spit things out. White holes are a perfectly valid mathematical solution to the equations of general relativity, but that doesn't mean that they actually exist in nature. In fact, they almost certainly do not exist, since there is no way to produce one. Producing a white hole is just as impossible as destroying a black hole, since the two processes are time reversals of each other. What is a wormhole? So far we have only considered ordinary vanilla black holes. Specifically, we have been talking all along about black holes that are not rotating and have no electric charge. If we consider black holes that rotate and or have charge, things get more complicated. In particular, it is possible to fall into such a black hole and not hit the singularity. In effect, the interior of a charged or rotating black hole can join up with a corresponding white hole in such a way that you can fall into the black hole and pop out of the white hole. This combination of black and white holes is called wormhole. The white hole may be somewhere very far away from the black hole. Indeed, it may even be in a different universe. That is, a region of space-time that, aside from the wormhole itself, is completely disconnected from our own region. A conveniently located wormhole would therefore provide a convenient and rapid way to travel very large distances, or even to travel to another universe. Maybe the exit to the wormhole would lie in the past, so that you could travel back in time by going through. All in all, they sound pretty cool. But before you apply for that research grant to go search for them, there are a couple of things you should know. First of all, wormholes almost certainly do not exist. As we said above in the section on the white holes, just because something is a valid mathematical solution to the equation doesn't mean that it actually exists in nature. In particular, black holes that form from the collapse of ordinary matter, which includes all the black holes that we think exist, do not form white holes. If you fall into one of those, you are not going to pop out of anywhere. You're going to hit a singularity, and that is all there is to it. Furthermore, even if a wormhole were formed, it is thought that it would not be stable. Even the slightest perturbation, including the perturbation caused by your attempt to travel through it, would cause it to collapse. Finally, even if wormholes exist and are stable, they are quite unpleasant to travel through. Radiation that pours into the wormhole from nearby stars, the cosmic microwave background, etc. gets blue shifted to very high frequencies. As you try to pass through the wormhole, you will get fried by these X-rays and gamma rays. Good day, this is Professor Will, CBMD PhD on astrophysics and cosmology. Well, this is the end of my session on black holes. Hope you enjoyed listening and have a great day.